Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We get started. Welcome to the session. The topic of this session is called data mining, and in fact there are two loosely coupled sections. First topic is about SQL Server 2005, a platform for data mining, and the second half of the presentation is about applying data mining in protein analysis. So my name is Hui Tan, and I'm the program manager for SQL Server data mining team. And joining me is the dev manager from our team, Jamie McNaney. So I will go over a few slides, and then Jamie will give you some demos, help you to have a direct understanding of our product. So, as many of you already know, SQL Server is way beyond a traditional relational database. Today, there are lots of components in SQL Server. Business intelligence is one of the key parts of the SQL Server. So let's see what we have in the business intelligence field. So first, the requirement for doing business intelligence is you need to integrate data from various sources. You need some tools to do data acquisition from different OLTP data sets. You also may apply some data transformations, analysis. For example, you may do some aggregations before the data is saved to the destination, or you may derive some new variables or new columns. So that's the part called data integration, or ETL. Once the data is gathered, you apply some analytics on top of the data warehouse. So the typical technology here is dimension modeling, multidimensional database, also called OLAP, and data mining, using statistic or machine learning techniques to analyze your data and dig out patterns. Last, you want to do some report. You want to publish the findings to a nice formatted way and send to your consumers, report consumers, either through email or through website. So we need to have a way to present data and to format the result of data. So those three areas, integrate, analyze, and report, we have different components inside SQL Server 2005. One box, we have lots of different components. So for the ETL part, we have SQL Server 2005 integration services. For the analyze phase, we have analysis services. And for the reporting part, we have reporting services 2005. And the focus of this topic is on the red part, data discovery via data mining. So it's the data mining part of analysis services. So Microsoft SQL Server is the first relational database product that introduced data mining inside a relational relational database package. So we entered the game in SQL Server 2000, 5 years ago. And the most work we have done is created an industrial standard, at that time called ODDB for data mining. Inside, there's an important language called DMX, Data Mining Extensions for SQL. The release is targeted for developer audience, and it was a version 1 product with two algorithms. One is Microsoft Decision Trees, the other is Microsoft Clustering. Both of them come from Microsoft Research. So there are a lot of research, there are some research articles written on those algorithms. During the past 5 years, we have invested a lot on data mining, and we will come out a product called SQL Server 2005 in a couple of months. That's 5 years R&D. So we really want to be the leader in the data mining space. We continued our efforts on data mining standard, HCI, for developer effort. We also have comprehensive feature set. We have data mining algorithms cover all sorts of data mining tasks, including classification, association, clustering, forecasting. All those areas we have different algorithms. And we also want to build a data mining ecosystem, which include data mining algorithm providers, tools providers, application developers as well as academic researchers who are doing data mining algorithms researches on top of SQL Server platform. So we think we will be the thought leadership in this area. So here are a few key messages. First, as I said, we have a complete set of tools. We have a lot of UI tools as well as algorithms. We have each algorithm has data mining viewers, and those viewers is embeddable in your own applications. So if your student want to build a data mining application, you can host all viewers inside, so save a lot of time for the presentation layer. We have integrated solution. So we consider data mining as a key member in the business intelligence family. Other members including relational data warehouse, OLAP, integration services, which is ETL, and reporting services. So we have tight integration. We are one of the few products which provide all the data business intelligence functionalities in one package. And we have deep integrations there. Another message is embedded data mining. We believe in the future there will be more and more applications which embedded data mining inside and make application much smarter. Just like Amazon.com today, if you buy one book, it gives you recommendations on other books, right? It's data mining application embedded inside a OLTP application on our website. And the last is data mining platform. So we think what our approach, unlike other small ISVs, is we are platform approach. We want to make our SQL Server analysis services the platform for data mining. In order to do that, we have to be extensible and flexible. We have algorithm plugin interface, which allows third party to develop algorithms and plug inside SQL Server, and to be considered equally as the rest of SQL Server building algorithms. We also have a lot of object models, management object model, development object model. Those object models allow users, developers to build applications on top of the platform, build web service, for example. So this slide shows the overall component architecture of SQL Server data mining. So data mining is part of analysis services. There are two components inside analysis services. One is OLAP server, the other is data mining. And this, on top of the slide, is a set of client applications or client object models. You can use ODDB, traditional ODDB to connect our server, use ADO, or use XML for analysis. Actually, if you use ODDB or ADO, it actually implicitly use XML for analysis. So the server and the client are communicated through XML method. And your client, that says your client doesn't need to be Windows. You can use a Linux or embedded client side to communicate with the Windows server. We have a set of interfaces which is integrated with data mining. For example, if you have a data mining algorithm inside of SQL Server, you can use ETL to invoke data mining to do a data mining flow. You can also use reporting services to build a report based on the result of a data mining prediction query. And the bottom here is the data mining interfaces. We have a set of algorithms, 9 algorithms from Microsoft. Most of them are joint developed between SQL Server team and Microsoft Research. We also have an API for third parties. So there are some ISVs specialized in data mining algorithms are working with us to provide some algorithms as a plugin. And if you or your students are interested in doing some projects, we can provide some technical assistance here as well, which allow your algorithm to be seamlessly integrated with SQL Server. And of course, once your algorithm is plugged inside SQL Server, you got a lot of advantages. You get advantages on all the API models. So developers can build applications, use standard API, connect to your data mining algorithm. And they can use standard query language, which is DMX, it's an industrial standard. Also, we also provide layers to connect to different databases, source databases. So you don't need to worry if the source is Oracle or DB2. It's treated the same. That layer is covered by our ODDB. So let me talk about DMX, data mining extensions for data mining queries for extensions for SQL. This is an initiative from Microsoft, started 5 years ago with a number of ISVs. And we try to build a query language which is similar to SQL for the data mining users. So developers, especially database developers, will be very familiar with this API and be easier to build, create data mining applications. So there are 3 types of statements. First, create a mining model. So this statement is very simple, just like create table. The create a mining model called create risk, and we have a set of columns. You specify the data type, the key is custom ID, and you have gender, income, profession. And the last one, risk, you have text for data type, discrete, and predictable. And the last part of the statement is which algorithm you use. So if you look at this statement, it's very easy to understand. It uses gender, income, profession to predict credit risk based on Microsoft decision trees. And the second statement is training. Once the model is created, it's still empty. So you need to train it. And the algorithm will discover patterns, and those patterns will be persisted inside the data mining container. So we use inserting to statement. Inserting to create a risk. You specify the list of columns from the mining model, and then you do a select statement. This is a part of standard SQL. It selects training data set from any data source, either from SQL or from Access or from Excel or Oracle. For the data mining analysis services, it's all equal. So training usually is time consuming. After training, you want to do prediction. And the prediction part, we model it as a select statement. So for example here, I select 3 columns. The custom ID, credit risk.risk, this is the predictable column from this mining model. And also predict probability, which is a predefined prediction function. Predict probability credit risk. And you join 2 objects. One is a mining model. It's not a relational object, but you can think about it like a relational table. And the other is the new customer table. You specify the column mapping here. So this statement returns 3 columns: custom ID, credit risk, and what's the probability of the credit risk. And you can issue this prediction query using ADO, and the result is in a tabular format. So it's very similar to any database applications. Connect to a database, send a relational query, and get result back in a tabular format. So data mining models analyze a set of cases. So these are the simple cases. I have 3 students. I know their gender, parent income, IQ, parent encouragement, and the last column is the predictable column, which is college plan. You know, some people are yes, some people have college plan no. So these are very simple. Most data mining applications does support simple cases. And we have proposed another way, which is more complicated cases. We call it nested cases. The reason is in many cases we find you have multi-value attributes. Customer bought a set of products or watched a set of movies. So you want to model those multi-value attributes. And this gives a lot of expressive power. For example, in this data set, I have 3 cases. Customer, their demographic information, plus the list of movies they like, plus the score they ranked these movies. I can predict customers' gender based on the list of movies they watched, plus their IQ and their age, for example. Or I can predict the list of movies they like based on their demographic information. Or I can predict the list of other movies they like based on the movies they already purchased or watched. So nested table helps you to model data, complicated business problem easily. And you don't need to worry of the pivot it. The algorithm, not actually the layer before the algorithm, the data mining infrastructure code will help you to pivot it yourself and give you all the correlation counts. So for you to develop algorithms, you can directly consume the converted data for you. So it adds expressive power as well as saves lots of time for each year. You don't need to manually create a very wide table with all those columns, binary columns. We have a rich set of algorithms, as I mentioned. We don't have time to go each of them, but most of them we have research papers. The first one is Microsoft Decision Tree. It supports both classification and regression. Clustering, we have two built-in clustering algorithms. One is k-means. The other is EM, expectation and maximization. We also support automatically discover the number of clusters within a data set. We have time series algorithm, and the algorithm is based on a research paper written by David Heckman. It's called ART, autoregression tree. So it uses regression tree technique to forecast the future values of a time series. It also finds correlations among different series. For example, you can build a model with 5,000 NASDAQ stock tickers for the past 2 years. And it finds out, for example, if their stock value has strong correlation to Microsoft's future value, it may end up using their previous value plus Microsoft's previous value to predict future value for Microsoft. We have sequence clustering algorithm, which is a hybrid of sequence and clustering algorithm. This is very useful for clickstring analysis. So each web page is a state of the sequence, and the transition is modeled using the sequence. And you can group customers or web visitors together based on their navigation patterns. You can also analyze it for purchase as well, or in academic, students which courses they take. Some people take the course in this order, some students take courses in the other order, and you can group them based on the similarity. Association algorithm, the one we use is a very classic a priori type of algorithm, but we have very efficient implementation. Then we have naive Bayes, simple naive Bayes, neural network, multi-layer Purchasing, and also the last we have text mining technique, which is also technique transferred from Microsoft Research Azure. It analyzes your English text and extract noun and noun phrases. Once it's convert the unstructured data to the structured relational format, we can apply naive Bayes, for example, to classify your documents. So now my colleague Jamie will show you some demos of our product.
See if I can get everything switched over here. Here we go. So my name is Jamie McLennan, and as always said, I'm the development manager for analysis services. And what I'm going to do right now is just give you a flavor of what we're offering in SQL Server 2005, so you can see a little bit maybe how you can apply it back at home in your research or your classwork, or also how maybe you can plug into this environment and what the advantages and some of the choices that we made. The first thing that you'll see is that our environment here is actually, this environment is Visual Studio. So our data mining environment is Visual Studio. And the reason why it's Visual Studio is that most of these projects where you're doing data mining, or if you're doing any other kind of business intelligence like an OLAP cube or reporting, whatever, you're actually doing a development project. You're developing something which you're going to want to share out. So just by being part of Visual Studio, that allows us to do some things like integrate with source code control and a lot of other kind of neat features which you have for that kind of environment. Another thing it lets me do is, if you're familiar with Visual Studio, is Visual Studio has a solution concept, and you see it says solution up there, and we have one project in there which I call AC. I can have multiple projects in there. I could have a reporting services project in there, which is where I'm going to show my results. I could have some code projects in there, which maybe are algorithms I'm going to integrate into this system, or store procedures that I'm going to write as other projects. Or I could have a web front-end project all inside the same solution. So it keeps it all together for the end user or the end development team that's going to be working on different parts, so they can all share the same thing. So that's kind of a really interesting feature just to begin with before we even get into what the data mining part is. Now what we're looking at right here, I already started the project, and I created something called the data source view. And a data source view basically is where you select your tables that you're going to do mining on. And what I did here, these are actually tables from a SQL Server database, but they could just be easily tables from a DB2 database or an Oracle database, or even an Access database, and potentially, Excel and many other different backends. We also support data mining from any source, because you can do data mining in integration services, which allows you to pull data from any data source and push it into your mining model. So I'm not going to be able to show that now. But if you want to do data mining of a flat files, you could do that directly in integration services. And also, with some tricks, you could do it in this environment as well. So the data source view environment allows you to manipulate your data source and kind of look at it in different ways. It also lets you, we have some rudimentary data exploration tools. So the first table is what we call a case table, and it just has the demographic information. This data is a movie survey I did about from people at Microsoft, just about their movie watching behaviors. And you have columns such as their marital status, who in their family picks what movies they watch. You see a lot of people at Microsoft, their wives pick the model, their wives or husbands pick the movies they watch, how often they watch movies, and so on and so forth, that kind of information. And then we have these other tables in here, such as this hobbies table. And if I look at this table and see what it looks like, it has basically two columns, the customer ID and their list of hobbies, right? So one customer has many hobbies, so it's kind of a one-to-many relationship in this table. And this is how we do the nesting. So this is how I can say I have a nested table. So for when I'm going to create my model, I'm going to have all the demographic information in there, but I also have the list of hobbies that this person likes. So it gives me a lot of expressive power. And it's actually very interesting the kind of things you can do it. For example, Correlated Health Services in Israel, they built a model to predict whether or not a senior citizen's health is going to deteriorate within the next year, using the previous 2 years of data. And to do that, they had all the demographic information, and previously, using other products, what they had to do is search all the other information, manually do, quote-unquote data mining, where you're really digging through the data, to come up with attributes that they had to figure out which of the 1,000 attributes they're going to use and put in their database and do mining on. Well, what they did with our product is they said, what, I'll just create a nested table of all the medications they're using. I'll make a nested table of all the types of specialists they're seeing. I'll make a nested table of all their chronic illnesses that we know about, and use those as inputs to my data to predict whether or not they're health. And they ended up having 10 different nested tables. So they actually, essentially, they crossed their information across 11 different domains to solve one problem. So it gave them a much bigger expressive power. So skipping ahead, I'm going to go right into our wizards, which help you create models. And I'll right-click here and say New Mining Structure, which pops up our data mining wizard. The first thing it asks is whether I want to do data mining against a relational source or a cube, and we'll just leave relational source selected. And now I go and actually list out the techniques. So here it lists out all the algorithms that we have in our server. Now actually what it does, it actually goes to the server and discovers a list of algorithms that are on that server. So if you wrote your own plugin algorithms, or your students wrote a plugin algorithm, or you bought a plugin algorithm from a third party, it would just show up on this list. You don't do anything, it just shows up on this list on the client side, and everything else works the same. So I'm going to just leave it with decision trees for now. Click Next. It asks what data source view I want, and now it says how I want to use the tables. The customer is my case table, and now let me just take a couple. I'll take the hobbies that they have and their favorite channels as nested tables. And I'll click Next. And now it tells me how do I want to use these columns. I can make this window bigger. This is actually a wonderful new feature which we didn't have before, which is just making dialogues bigger. It's an amazing feature. So I'm just going to click here and just make everything input here. And what I'll do is I'll make the channels and hobbies inputs as well. And let me go and say, let's try to predict whether or not somebody's going to own their house. Let's predict how often they go to the movies at the theaters. And we'll also predict their favorite hobbies. So one thing that's kind of interesting is one thing we've done to make data mining easier is kind of wipe out a lot of the predefined, kind of the ideas about data mining. So normally in data mining product, I couldn't go and say I want 3 predictable targets, right? But here I can say 3 predictable targets, we'll just handle it. Another thing that we do is our clustering algorithm. This is the same dialogue that you'll get if you use our clustering algorithm, our association rules algorithm. It's not specific. So we can actually do predictions with a clustering algorithm. If anybody's used clustering before, they know it's not very great for predictions, but you can do it. It's not something we prevent the user. And then down the road, we have accuracy charts that tells you that the clustering algorithm probably didn't do a very good job unless you're predicting against your source data. So I'll just go ahead and click Next here on this data. Here it lets me select the content type, let it know whether things are categorical or continuous, and the data types, and I can go in here and hit detect, and it'll run a little heuristic which says, you know, if it only has 2 values in it, it'll make it discrete even though it's a numeric data type. I'll click next here and I give it a name. So my mining structure, I'll do the same name. My mining model inside the structure, I'll give it another name. Customers DT for decision trees. Now what I have here is a reduced view of my data source view, just what I've seen before, in the columns of my model. I'm not going to go to a lot here, but this is the mining structure, which is a new term. We also have this idea of a mining model. A mining model lives inside a structure, and it says, take those columns and those data bindings that I chose before and associate them with some data. Associate them with an algorithm, right? So I can go in here and say, here's my algorithm decision trees. I can do funny stuff like go and set all our nice set of advanced parameters for people who like to tweak that kind of stuff, and change how the columns are used. I can go in here and do something, but let's create another mining model, and I'll call it customers CL, and I'll use the clustering algorithm, and click OK. Oops, I use association rules. No, I don't want to continue. Let me try that again. Customers CL, and use Microsoft clustering. There we go. And then I'm also going to create another one, and I'll call it customers naive Bayes. Naive Bayes advertise in its metadata that it doesn't support continuous variables, so it tells me that continuous variables aren't going to be supported. So do I should continue? Yes. And you see that those columns that are continuous that marked as ignore. So what I have here is one mining structure. I define kind of the domain of a problem, and then I can have many different instances of models in that solution. Now what happens actually is it reads the data once and it puts that into a nice compressed cache, and then it feeds that to all those algorithms in parallel. So it kind of gives some advantage of parallel processing just at the top end. And then if you have your own algorithms, you can put those in here too, just like anything else. There's nothing special about a Microsoft algorithm versus a third-party algorithm. So another thing I'm going to do here is actually for the clustering, I'm going to go ahead and ignore these nested tables just for our sanity's sake. And then what I'm going to do is deploy this to the server. So really what I've done so far is I've created these files on my hard drive, which just have the XML metadata of those models and of those objects. And now I'm going to deploy it to my server. It creates the objects on the server, it reads the data, and then goes ahead and processes all the models. And this is the point in the presentation where we just say, tell everybody to watch the spinny. Little hypnotic little device that we have here to say, buy SQL Server, buy SQL Server, buy SQL Server. We're actually going to come up with a whole line of spinny t-shirts and stuffed animals. So it processed all the models, and now let me go ahead and browse some of these models. So the first thing I'm going to do is browse my decision tree model. And that's no. And here's our decision tree viewer. As Zoe said, you can take these viewers, you can put them in your own applications. Since you're creating your own algorithms too, you can actually write your own viewers and plug them in here. I can actually write my own tree viewer and have it replace this tree viewer for the user if I want to, or I can take this tree viewer and view my models with it using my algorithm, or write my own completely new viewers as well. So we have a lot of nice little features here. You can go back and forth. You can shade things by where this hobby is. This is acting in theater, the tree for acting in theaters. And you can see that the most concentration is where the Hobbies Museum and Arts exists. And one thing also you see here is if we look at it, we have museums and arts, which is a hobby, movies and television, which is a hobby. Then we have marital status also plays in. So you can see the interplay between the demographic information and the transactional information right here in the models. Now, there are multiple targets. Like I showed you, I clicked 3 things as predictable. Well, it's not just 3 things. Actually, every hobby becomes a predictable target. So when I look at here, I see I have a tree for every possible hobby. So I can go down here for business and investing, and I see I have a tree for business and investing. I can go to tree for comics animation, and so on and so forth. And I can see all these different trees. Well, another thing viewer we have is a dependency network, which kind of lets you see the forest for the trees. And just take a second to come up. I always have to use that line because it's decision trees. And you can zoom in here, and you kind of see the relationships. You can drag this down, see the strong relationships, like what's related to museums and arts. Bring that up. You see books and literature, photography, acting and theater are the strongest things, followed by news and media, and so on and so forth. So you get some good ideas of how that works. Let me go and browse our clustering model. Our clustering model is really nice because it kind of, you look at it and you're like, oh, okay, well, what's that? That's neat, but so what? So what it really does is it takes all our clusters, which are kind of abstract, and throws them on a surface and says, let's try to get the clusters that are similar, close to each other, and the ones that are different, far apart. So cluster 6 is probably not very similar to cluster 5, but you know, cluster 1 and 5 might be close. And also you see that cluster 1 and 2 have more people in them. I can also go in here and say, for example, where are the people who own their houses? Well, these are the people that own their houses. These are the people that rent their houses. Where are the people with let's look at theater frequency. People who go to the movies daily, well, that's nobody. How about people who go to the movies monthly? Almost every cluster has a good concentration. Weekly, only these guys over here are going weekly. So you can kind of get a view of your clusters there. And there's lots of other views as well. I'm not going to go into them all just for time's sake. But we have a nice view here which says, show me the difference between cluster 1 and everybody who's not in cluster 1. And this is applicable to everything. Actually, there's a paper written on SQL Server 2000 using our clustering algorithm where they did something, a scientific study based on the impact of underwater wood on greenhouse gases, which I don't really actually remember the results of the study, but they said they did the study previously using manual methods, and it took several weeks, if not months, and they did it using our clustering algorithm, and they did the same research, got the same results in about 3 days. So it's very, very nice. Now I'm going to skip the accuracy chart so we can move forward, and just go quickly over to our mining model prediction pane. Now prediction is where we think that, you know, there's a lot of benefit. You can do predictions, you can embed predictions in applications. There's lots of different things. And actually one thing I always mention is I think there's two sides of data mining. There's descriptive analytics. That's showing you what I just showed you now. Data mining did it. It showed you a bunch of stuff that maybe you didn't know before. And then there's predictive analytics, which is applying that against new data, which I'm showing you right now. So I'm going to switch this over to Singleton Mode, which allows me to actually enter in values. And what I want to do is I want to say, what are possibly the top 2 hobbies that people are going to want. Actually, let me delete that. Delete that. I'm going to say, give me a prediction function where I'm going to predict hobbies, and I want to say, what are the top 2 most likely hobbies for a person? And I'll just go in here and say, the person's 35, they have a bachelor's degree, they're male, their other hobbies are, say, camping and computers, and they own their house. What this does is actually just generates a query, like Zowie showed you, which says select the top 2 hobbies from my model, prediction, join, there's my input. Right? So it's very simple, very easy to create this kind of stuff. And there's a lot of things you can send here. I could send, at this point, I can send a singleton query like this. I can send a query to a relational database. I can send a parameter from the client, so I can have my data gathered on the client and send that as a row set parameter to the server. I could have another data mining query in there where I predict from another model and send the output of that model into a different model. So there's a lot of flexibility you have there as well. So when I look at the result, I don't know what the result's going to be, and we'll find out that we have this nested result. Actually, let me just go back here and just for fun, so you can see, kind of get an idea of what it looks like. Let's actually take the age and put that here as well. Okay, it's not letting me do that. Okay, let's go here, and I'll say, comma, t dot age. And if I look at the result now, you see I have my row, my case row, and a nested table of the results, and it says that this person is likely to watch like science, technology, and travel. And if I go back to my design, I can go back here and change my hobbies, change it to, add acting and theater, fitness, food and cooking, and get rid of camping and hiking, and change, let's say, make it a woman with a master's degree who's 40, and then hit the results, and now it says books and literature and science technology. So you can get different results. You can do a lot of what-if kind of analysis here. You can take these queries and embed them into your results. So the idea here is to give you an idea of the flexibility of the platform. There's a lot of other things you can do with the platform other than this. When you write your own algorithms, you don't worry about that language. Our infrastructure basically takes all the data from whatever data source, creates a stream of active value pairs and sends those to your algorithm. So all your algorithm has to deal with is a stream of active value pairs. and it's up to you to do with that. The only thing difference between, I would say, our implementation of an algorithm in our system and then implementing an algorithm on your own is that generally people don't have to worry about cases of different lengths. So if you're writing a data mining algorithm, usually you think of the old model, which is kind of the square model, so you know that your cases are all going to have 10 attributes. If the first case has 10 attributes, well, in our case, you could have thousands of attributes. And actually, we've run models where we have 750,000 attributes, and they run just fine. So that's the demo of SQL Server 2005 data mining, and I wanted to transfer it over to Wei Wang, who's going to talk about her data mining work with protein analysis. Thank you. Yes?
What about the model combination? Does it allow model combination back in boosting?
Currently, no. But you could actually write an algorithm which calls the other algorithm that does the backing and boosting for you.
What about publishing, let's say, a specific function in web service?
Yeah, actually, since everything is an XML for analysis, everything's automatically a web service. You just have to open up the port, the HTTP port, to on your client, and it is a web service. If you want to write this down, there's a website called SQL-Server-Datamining.com, and on that website we actually have an XML for analysis example where it allows you to, it reads all the metadata and comes up with a query builder, and you can click what you want to query, and it'll send an XML request and get the XML response. Any more questions?
So if you want to put your own algorithm,
Yes?
is that reasonably easy?
It is reasonably easy. It's much easier than we had in SQL Server 2000. Actually, the API level where you write your algorithms is at the exact same place at the API level where the Microsoft algorithms are written. So they have no more or less functionality than the Microsoft algorithms, and it's a much lower level API. We have it right now. The API is a COM API, C++. It's not, you don't have to worry about COM stuff. It's just all in process. But we also are working on a sample for a managed code, a C# or VB.NET kind of implementation as well. That'll be released as a sample on how you can write code that way.
We do have a tutorial available in SQL Server.
SQLServerDataMining.com. One question? Okay, so the text mining that we have, the question is, can you explain more text mining? The text mining that we have are two transformations which are in integration services, and it's a transformation for term extraction, which finds the noun and noun phrases in your English documents, and then term lookup, which takes new documents and says, you know, this term belongs in this document. It does word stemming, and it does a couple other things. It actually finds key phrases, so it doesn't necessarily find just one term. It can find many. It'll find data mining as one term instead of two separate terms. And then you can actually pump those into your OLAP cubes or reports or data mining models.
Daniela and I will be here during the break. More questions.
Are you ready?
Yeah, we're going to get.
Okay. We'll take questions afterwards.
Okay, so for the rest of the next half an hour also, I'm going to share with you a project that partially funded by the eScience Application Award here. And the project is called, can you hear me? The project is called MotifSpace. Basically, first I will give you an overview about what this project is about and how computer science actually and research can help greatly in bioinformatics applications. Myself came from the background of database and data mining, and during the past 3 years I started to look into bioinformatics applications, and primarily as a driving. I started with as a driving application of my research in computer science, and since I started to do that, I become more and more interested. And this is just one project I have currently working on at UNC Chapel Hill. During the lunch session, I talked briefly about mining mining patterns from protein structure. As I mentioned before, that proteins are the machinery of life, and the next big challenge that biologists try to address is to determine how protein functions. And we all know that the protein's function is determined by its structure, and therefore the scientists have been working on cataloging new protein structures at a very actually at an exponential rate. and currently all the structures are deposited into a protein data bank. This is a publicly available, actually distributed data resources that anybody who's interested can look into that. You can see that the rate has been growing exponentially. So if you look at a protein structure, I'm going to share a little bit more detail with you. Actually, it is a large molecule. Basically, it's a long linear chain of amino acids, and they fold into some stable but dynamic three-dimensional shape so that it can function and in a relatively stable state. We also know that for many of the proteins, actually only a small structure in the protein directly responsible for its function, and we often refer them as spatial motifs. Here is just three examples of proteins. Actually, they're coming. I just take three samples from three different protein structures, and the highlighted area are the functional site, actually sometimes called active site of the proteins. You can see that they are just formed by a very small number of amino acids, and it serves as the functional site of the protein. And from now on, let's refer them as spatial motifs. And our emphasis in this project is to develop a computational method to fast and efficiently discover all those spatial motifs, so that the biologists can use them to form valid hypotheses for their tests. So the overall structure of MotifSpace actually consists of several computational components, and we start with the protein structures available in protein data bank. And we all know that scientists have been doing a great job in grouping protein structures according to the similarities in their structure and the functions. Here is on the right-hand side it's just the high-level protein classification actually in scope. It's based on in this particular one, it's based on structure similarity. So given any protein family, what we can do is we have a motif manner. Basically, it takes the protein structure out of the protein data bank and look for recurrent spatial motifs. So basically, they are the motifs that occur at a very high frequency within this family. And the next step is to apply a filter on those spatial motifs, just to select out those ones that occur rarely in the rest of the protein world. So the notion here is that we want to find something that's highly associated with this particular protein family that we want to study, because we want to find out what are the characteristics of this protein family that are responsible for example, for the common function shared by this group of proteins. We want to be able to understand how they function and which part corresponding to their actually responsible for their function. So we call them family-specific motifs, and we deposit the motifs in a database. So, and then these motifs can be used to construct predictive models and to predict, for example, protein functions. So a new structure comes in and go through this classifier, and then we will be able to tell whether or not this, how likely this new structure has this particular function. And we'll also look at the literature in biomedical domain and to look for actually to extract experimental knowledge that has been developed by scientists and put them in a knowledge base. And in order to make full use of this, the information and knowledge we discovered, we will have a motif navigator. Basically, this navigator will talk to each individual component and enable a user to interact with them. And if you look at the whole picture, you can see that there's several important components that constitute the whole project. And if you look beneath each of the components, you can see that actually these are the area of research that involved in each component. Okay, you can see that in the motif mine, actually, I'm going to focus on today is on subgraph mining, and then for the next one is the motif filter. Actually, it's associated with feature selection, association discovery, and to build the classifier, we use classification. Then here, the next one is the information retrieval and text mining, and the last is largely, the navigator can benefit from novel visualization technique. Actually, these are the areas that we're currently working on, and to develop novel computer science research. So I'm just going to share with you this motif miner, and if time allowed, I'll show you a brief demonstration to see to show the idea. So let's go back to the protein structure available in protein data bank. In order to analyze them, we have to be able to represent them in a clean and precise way. So in protein data bank, if you look at the data file, actually they are represented by points in a three-dimensional space. What's available there is for each item in the protein, you have 3D coordinates. You can think that what's the input to the whole system is a set of points with their three-dimensional coordinates. But what you need to keep in mind is that they have errors and noise there. It's just like you have a protein structure and then you take a picture of that. And then for each point, you have its location within some error bound. So starting from that point, and then in the motif space, the first step, what we're doing is to represent the protein structure so that we can keep the essential information for the mining of spatial motifs. What we're choose to do is to represent by graphs, where nodes corresponding to amino acid residues and edges corresponding to potential interactions. And we're investigating the trade-off between the complexity of the graph and the information we need to capture. And you can imagine there's many different ways to construct the graph to represent the protein structure. And for ourselves, we have tried several different approaches. And next, I'm going to share with you one of them. But no matter what way you decide to represent your protein structure by graphs, after you have done this, actually, spatial motifs that I showed you before, actually, one of them is also highlighted on the top left figure, actually can correspond to a subgraph in the graph representation. So basically, you can see once we establish this correspondence, the exercise of mining spatial motifs becomes finding frequent subgraphs in a set of graphs. And the challenge here is subgraph isomorphism, which has been proven to be NP complete. So next, I'm going to share with you how we are going to actually what we have been doing is to make a few key observations of the protein graphs that allow us to develop some efficient algorithm. Before I go into that, I'm going to show you just one way that we have used to represent protein structures by graphs. It's called almost Delany. Actually, it's developed by my colleague Jack Snowing and his student at UNC Chapel Hill. And their paper actually is computational geometry research, and their paper published last year showed up. What we're doing here is that you can see one way to represent it. Before I show this, I want to emphasize that this is not the unique way to represent it. This is just a reasonable way to do this. It turned out to be, can give us quite good result. So what we're looking at here is that if we select 4 points in a three-dimensional space, and then we look at whether or not we can form an empty sphere that those 4 points happen to pass through the surface, and with of course no other point included in this empty sphere. If that's the case, actually we can connect each pair of these 2 points with edges. So the notion here is that we want to define some kind of spatial neighborhood with no interference of another point. So that's why we want this empty sphere. And as I mentioned before, well, that's the standard definition of Delany tessellation. as I mentioned before, there's noise in the location of each point. So therefore, we want to allow some kind of error. And what we're doing here, we call it almost done. And basically, we allow a parameter. We have additional parameter epsilon. Basically, that defines the maximal error that we allowed per point in terms of their location. So basically, we allow each point to perturb towards any direction by an amount of at most epsilon. And if given that flexibility, if we can still construct that empty sphere, then we think that there should be an edge there. So by this definition, you can see that the traditional representation of design tessellation is just a special case with epsilon equal to 0. So this is just an animation to show you that after you move, you allow yourself to move the point around, and there's a possibility of constructing new edges. So this red one is just a new edge that allowed if you allow some perturbation. So if you vary this epsilon threshold from 0 to positive infinite, so basically you can allow them to perturb in any way you want. And then you look at the edges with distance less than a certain threshold, then you can find this interesting graph. Basically, once you allow more errors there, you're going to have more and more edges in your graph. And in our experiment, we use 1.0 as our default value. So after we represent the protein structures by graphs, now the next question is how do we find spatial motifs, which is how do we find subgraphs that are corresponding to the spatial motifs. And we form this as a graph mining problem. And in this case, we want to find frequent subgraphs because we want to find spatial motifs that occur in almost every protein within the family. But of course, the next step is it has to occur rarely in the rest of the protein world. But first, we want to find out those ones that occur frequently within the family. So this is actually exactly the frequent subgraph mining problem. And for those of you who are not familiar with the problem, basically it's just one chart to give you an overview what the problem is about. If you start with a graph database of 3 graphs, and then you set your threshold as 2 out of the 3. Basically, you ask for all the subgraphs that occur in at least 2 out of the 3 graphs. So on the bottom of this, these are all the subgraphs that occur at least twice in your database. So this definition is very simple, but if you think about the computation behind this, it's very complicated, and it's very time-consuming. So a lot of our effort has been investigating how to develop fast and efficient algorithm to allow this kind of computation. One of our approach is based on canonical. We define some canonical form to represent the graph and the subgraphs, and so that we can have some nice property on that to allow some computational speed up. So this is at a high level. We use a canonical adjacency matrix, and we define it as if we look at adjacency matrix, is basically if you lay out the node in the graph along the diagonal, and then each entry is corresponding to the edges that connect those 2 nodes, and we put 0 there if there's no edge there. So it's a simple representation. It's an adjacency matrix. And you can see that for a given graph, the adjacency matrix is not unique. You can have many different adjacency matrices, one corresponding to each combination of your node along the diagonal in the matrix. And what we defined, the canonical one should be the one that maximizes some function, and in this case, it's a code we define. So we concatenate row-wise the adjacency matrix. We want to select the one that maximizes this coding. And in order to put this order, we define in this particular example, we just say, well, it's alphabetic order, lexicographical order. So that, but in the real world, you would have different ways to define order between amino acids. So if that's the case, actually the leftmost one is the one that corresponding to the maximum coding, and we call it canonical adjacency matrix. And which is this one. Oh, okay. So after that, basically all the subgraphs, the frequent subgraph we're interested in, would naturally be represented as in the tree structure. Basically, each of the entry in the tree corresponding to a subgraph and can be represented by its canonical adjacency form. And due to the time constraint, I'm not going to be able to share with you the details, technical details of how this can speed up, but I'm just to give you a high-level summarization. So, as I mentioned to you, that we use the graph representation for protein structures, and we're use the edges to encode potential interaction between amino acids. So, which means that the graph reconstruct has some spatial locality. And basically, you will not connect amino acids that are further apart. You're only interested in those ones that are in some spatial neighborhood. And this would translate into a nice property of a bounded degrees in the graph. Also, we use the a priori property that can be applied to any frequent pattern mining algorithm to help us to guide our basically mining of frequent subgraphs. And the basis says that any supergraph of an infrequent subgraph is infrequent. So basically, this would suggest that we need to check on small subgraph first before we go to bigger subgraph. And this would help us to eliminate unnecessary isomorphism check. And as I showed you, the canonical form we're using, which allow us to reduce the avoid redundant examination. And we use that first exploration of all possible frequent subgraphs, so that we can use we can employ some incremental isomorphism check. Basically, we want to reuse the result on smaller subgraphs we have checked before, so we don't recheck it. And also, this also allows for some for better memory utilization. So so far we have developed several different versions of our subgraph mining algorithm that's especially tuned for mining spatial motifs out of protein structures. Basically, we utilize some special property. You can see that these are not general graphs. If it's general graphs, then it's already been proven that the subgraph isomorphism is anti-complete problem. But especially due to the fourth property that we have, this would allow us to design very interesting algorithms that do not force ourselves to be in such a dilemma. So now what we are doing is we want to incorporate more interesting features to our algorithm. One of them is we want to allow substitution of amino acid types in the subgraph we are considering, and we want to support more dynamics and the geometric constraints. So here, before I show you the demo, I want to give you a few examples that we tried along our path and for the past 3 years. Actually, the first protein family we studied is serine processes. And in this table, I think this is 38 motifs that we discovered that is specifically to this protein family. Actually, I plot them in one of the protein structures. You can see this the colorful balls. They are the amino acid residues part of the spatial motif. And we have 38 of them. You can see that there's actually many of the spatial motifs are heavily overlapped with each other. And if you look at that, the center part, actually that's the active site of this family of proteins. This is the pattern, actually spatial motif that we discovered based on the scope. Actually, the set of protein we are using is classified by scope version 1.65, released by the end of 2003. And since then, there's new structures become available, and we use those ones as a test. And these are the 7 proteins that whose structure are available after that. And these are actually our protein classifier identified them as labeled them as serine proteases. And then we go ahead to check each one of them and find out actually all of them are actually serine proteases, even though they were not originally labeled in the scope by the end of 2003. And actually some of them are currently labeled as serine proteases officially in scope. There's just a new release of scope. I think it's 1.67. And after this success, we go ahead and say, well, whether or not it's because we just had luck in that one particular family, or this general paradigm can be applied to all the protein families. And if that's the case, then there will be a lot of potential in help biologists to design their wet lab test. So we go ahead to test another family, which is the cysteine proteases. And these are the family-specific proteins, family-specific motifs we put out. And actually, if I don't know whether or not it's visible from your side, is the yellow, the highlighted, the residues. Actually, they are the active center of this family. And I want to mention that actually for all this exercise, and we didn't incorporate any of this domain knowledge. We just look at the structure of the protein, and that's all the information we use for the mining exercise. And then we look at, okay, what are these spatial motifs, and whether or not the result makes sense in biology. So on the left-hand side, actually these are the I highlight these are the active sites. The motifs involved in this cover those active sites. And you can see that in this in one function, actually, this exactly corresponding to it's just a different, maybe slightly different orientation to the one figure in the right-hand side. Actually, we directly took out this figure from this paper. They reported those. These are the important structure that's supporting the active site. And so. If we zoom back so that we can see all these spatial motifs we put out all together and see what are they, and what we just look at are this part. These are the active sites. And what are this part? Then that's the natural question. And then we found out actually these are the hydrophobic binding pocket, so which also carry the biological function. So we're pretty happy with this. If we have time, I'm going to show you a little time just on this particular family. So after that, well, we'll go ahead to try something more interesting and actually more adventurous, which is function inference of orphan structure. So you know that there's exist many protein structures that people don't know, just have no idea about what are their functions is. And we want to use, of course, we want to use our computational means to try to infer what are the possible functions they carry. And this is just one example we have tried. On the left-hand side is a family called MDH, and we found 49 spatial motifs that are specific to this family, and these are highlighted in the middle of that. And on the right-hand side is an orphan structure that actually was a task 5 target that people try to predict the fold and the structure of the protein. Now we know the structure, but still we don't know the function. And that because there's no good sequence and structure alignment to any of the known protein. So it still remains a puzzle. And what we found out actually, this particular protein contains 30 out of the 49 spatial motifs that we found for that family. And there's just a recent literature reporting that actually some biologists found in their wet lab test that this particular protein looks like carries a function similar to that family. And they report in one of their recent papers. And this is a second example we have. Actually, this is a different protein family, and we have 62 spatial motifs found. And actually, this family is a very small one. It only has 4 members at the end of 2003. And this is, again, another orphan structure with unknown function. And still, it's not classified yet with any function as of, I think, a few months ago. And we found out actually this particular protein contains 46 out of the 62 spatial motifs we found associated with that family. And the more interesting is, like, we found out there's actually several proteins, new proteins that people just discovered, actually have some structure similarity with this particular family, and they all already been officially labeled with that family. So there's some evidence to suggest that the prediction model we are building can be served as a very good model to generate hypotheses for the biologists to design their wet lab test. Okay, so if you're interested in the data mining and the bioinformatics techniques that we are developing, these are the list of papers that we published recently. And of course, this project, part of the success was that the participation of the collaborators from different fields to make this happen. So now I'm going to show you a little demo. Okay, so I'm going to load 7 So these are 7 proteins from 15 proteases. And save the time, I'm going to set my threshold in pretty high. So I'm looking for spatial motifs that occur in at least 6 of the 7 proteins. And we want the spatial motif have at least contain 6 amino acid residues. Then I'm going to submit the job. So what is happening here is that this application would go back to a server at UNC, which directly calls the protein data bank to retrieve all those structures. And because everything is computed on the fly, so that's why you see actually we have to wait a little bit until the results returned. So what it does is that once it retrieves the structure, basically for each protein is a list of coordinates associated with each item. And then we construct the graph, and then we use a graph mining algorithm to mine frequent subgraphs, and then we map them back to the protein world, and then actually in the middle block, right now it's empty here, it would eventually, hopefully, show a list of motifs that actually is showing up now, and that's shared by this at least 6 out of the 7 structures. So if we select one of them, actually we can see what are the motifs that contained by this particular family, and then if we want to see where are they and how they look like, it just takes a little bit while. Okay. So these are this highlighted area. These are all those spatial motifs, and actually this contains 2 out of this group are the active center of this family of proteins. And if you can look at it, these are the list of the motifs. And you can even highlight them or disable them and look at them each one after another. So now I also want to show you that, let me see. So if I choose 2 of them, I can see that what are the things shared by this. And if I want to just see whether or not I want to show two protein structure together, aligned according to the spatial motif I find out. Actually, the red one is the one that I just showed you before, and the magenta one is the second protein. So actually, you can see that this is it may not be very visible here, but so in that area, that's the motif and the spatial motif that I'm interested in. I use this to align these two two protein structure. Actually, this particular motif that covers the active site of the protein. You can see that actually in this particular example that the second protein hasn't aligned pretty well with part of the first protein. The first one is a big one, and the second one is just a smaller one, and then they happen to be aligned pretty well if we align them based on their active. The spatial motifs that cover the active site. And in general, if you play with this and with other protein families, and you would see that in general, two proteins may not align very well, and globally. So part of them align pretty well, and the rest of the part may be just branch out, and because if they align pretty well, it always align well, then you can easily find them by global structure alignment. So the beauty of this project is that it does not require that. As long as part of the protein structure shows some similarities, we just pull that out. You can see that computationally, it's much more difficult to support this kind of local alignment. And this is what we can support. In this case, actually, this is just showing you one example of the spatial motifs that we're able to find out. And you can see that this little part is the active center. So, any questions? Okay. Please.
I have two questions. They both arise from a computer scientist working with biologists.
Okay.
One is about the culture, is that very good biologists tend to see computer scientists as harnessing the power of computing to confirm their science. And can you speak a little bit about whether or not you've been able to get your biologist friends to see your system as a hypothesis management system, generating new hypotheses? With that in mind, have you got any insight into looking for meta-motifs or insight from biology on looking for clusters of motifs which talk about sort of mega-function proteins?
Yeah, I think that's a very good question. So when we started this project, I talked to my collaborators from the other side very frequently, and I'll see 90% of the time their reaction is kind of negative. Basically, I show them what I do, and they say, no, we're not interested in this, we're interested in something else, which is always different from what I show them. Even though I thought that, oh, you said you're interested in this last time, how come you change your mind? And then they always say, oh, that's not what I mean last time. So basically there's a learning curve there that allow us to communicate. So at the beginning, of course, that's when I show you a couple of examples, like how it is happen to sort of like the spatial motif contains the active. So basically all those proof of concept to give them the confidence that, this is a good system to use. Because for them to design and implement their experiment is very costly and tedious and take a long time, and they don't want to sort of like take a random hypothesis. So they want to have some kind of confidence before they go ahead to do that. But I'm happy to say at this stage, we have developed some kind of bond and trust, so that that's why for the later part, the one I showed to you is on the functional inference. Basically, nobody knows what the function of those orphan structures are, and then when we were able to show them to the biologists, they're very interested in that. So because of all this other work that we have done in the past, but just to sort of like rediscover what they already know. So then now they feel more and more confident that they want to use this one as a way to help them to generate their hypothesis. So
the technical question is about mental motifs and using biological knowledge.
right.
You add extra knowledge about how the motifs combine and are actually dependent in the protein molecule.
I want to make sure that I understand your question. So when you mean meta-motif, it's a motif that's formed by multiple. Actually, we have looked at that, and even I can, let me see whether I could have something to see. I even have a backup chart for this. So these are the, if you look at the green and red, there's two motifs we discovered. And if you look at on this 3D structure, actually they bound it to each other. And the only reason that they are discovered as two motifs is that there are some flexibilities there geometrically, so that if you look at different proteins, so that they won't be able to be covered by a single motif. But they have actually after we find out this motif, we also look into associations among those. And so what we do is that we can treat each motif as a feature, right? And the simplest way is a binary feature, and then basically each protein can be described by a vector. So motif A is on and B is off, and then we can use association or feature selection, all those techniques we have tried to see whether or not there's strong association among different motifs, and we found some of them. And they have them, actually we call them meta-motifs. Right. Yeah. Yes. Yes.
How does that correlate with known active sites? Have you tried to do a correlation between your sort of computational method of finding small motifs, because the protein data bank is already labeled with active sites.
Right.
And so there are many, many active sites that are known and their functions are known, and then biologists look for those active sites in proteins. So what is the relationship? Have you tried to combine the two, spatial motifs with biological active sites, to improve your discovery process?
This is a good point. And what we have been doing is that when we did this intentionally just to prove to biologists that this is a quite effective way to mine the spatial motifs and provide them with some nice hypotheses to test. And so when we do the mining, we didn't incorporate that knowledge. We just treat all the residues as the same and look at their geometric features and see whether or not we can find spatial motifs in that way. And then after that, we validate each of our spatial motifs and gain some domain knowledge. And some of them are, if there's things available at PDB, then that's easy. We look at them. And some of my students also spend a lot of time to just look into the papers available from PubMed to see whether or not there's some explanations in some of these papers that happen to report, okay, here's the functional side, or here's some interesting things going on, and then that's what we have been doing. Of course, our next step would be like, actually we start to think about this, the ways like to incorporate domain knowledge into the mining exercise. So that's something on our agenda, but we haven't got it finished yet. That's good. Actually, this is what interesting. What we're doing is the little demo I showed you is a way that we align two protein structures, and we are in the summer we have been starting to work like to build a nice and a systematic way to align multiple structures, and with the goal of provide the user with a nice visualization scheme, and so that they can explore all these motifs. Thank you.